All right, so continuing with example 3.14, I did notice I made a slight mistake in this last calculation here. I forgot to carry this negative over here. So our time is going to be different here. So let me go ahead and take that into account. So if we have 4.9 plus 44.1, and divide that by 9.8, we get a negative 5 seconds, but again, time is positive. So instead, we're going to say 4.9 minus 44.1 divided by a negative 9.8. And so we get 4 seconds as our time, which makes more sense, right? Okay. So with that, we can move on to part B. What is the velocity when it arrives at the ground? Okay, so we want to find our final velocity. Okay, so we'll need to come back here. And our final velocity can be calculated with this equation here. So final velocity, I'm just going to go ahead and squeeze it in up here if I can, is equal to V naught minus GT, I believe it was. I'll go ahead and make sure. Yes. Okay. So our initial velocity was 4.9 meters per second, and it is negative, minus 9.8 meters per second squared times our time, which we solve for as 4 seconds. And so we get, let's see, 4.9 minus 9.8 times 4. That gives us a velocity of negative 44.1, which matches with this figure here. Okay? All right, so I'm going to go ahead and move on to another example. This is example 3.15. It states a batter hits a baseball straight up from home plate, and the ball is caught 5.0 seconds after it's struck. Okay. It asks, what is the initial velocity of the ball? So we know the time is 5 seconds. Okay. We want to find the initial velocity. So let's go back here. Let's see. We may need to look at that figure. I don't have it up. Let's see. Okay. Okay. So the ball is hit straight upward, and it is caught at the same position. So y equals 0. Okay. Let's see here. So delta y is 0. Let's see if it gives us anything else. It does not. So delta y looks like it is 0. We could, we're looking for the initial velocity, so we can say y equals y naught plus v naught t minus 1/2 at squared, or gt I should say, and solve for v naught. So, whoops, okay, whoops, sorry about that. So, v naught t equals 1/2 gt squared. Solve for v naught, we get 1/2 gt. And we can plug those numbers in. So 0.5 times 9.8 meters per second squared times our time. So this should be 24.5 meters per second is our initial velocity. Okay, so now looking at part B, we want to know what the maximum height is that the ball reaches. So at this position, okay, at maximum height, our velocity is going to be 0. Okay, remember when we were looking at the tennis ball, the maximum, the tennis ball stops and starts to fall back down. So that's the same idea here. So we have our velocity is 0. Okay, so we know our initial velocity. We just solved for that. We know our time. Okay, our initial y is 0 in this case. Okay, so we can use this equation here, since we don't know what time it reaches that max height. Okay, so v squared equals v naught squared minus g delta y. So v squared equals v naught squared minus 2g and y minus y naught. Okay, so we can rearrange this. Remember our v is 0 here, so we have 2g times y minus y naught equals v naught squared, and solve for y. So this is 0, so we can cross that out as well, and we get v naught squared over 2g equals y. So if we plug our values in here, y equals v naught, so 24.5 squared, divided by 2 times 9.8. Plug that into our calculator. 5 squared over 2 times 9.8. We get our maximum height is 30.6 meters. Okay? All right, now part C. Sorry, my dog is growling at me. For part C, it asks how long does it take to reach the maximum height? So how long does it take to get there? Okay, let's look at our equations. And we can use this equation here. Okay, so that's like the same one we used earlier. So our maximum height is 30.6 meters. We just solve for that. So we have y equals y naught, which is 0, plus v naught t minus 1/2 gt squared. Okay. You can plug everything in. So I'm going to go ahead and move things over. We're going to have a negative 1/2 times 9.8 t squared plus 24.5 times t and minus that maximum height, 30.6. Okay. So we will use our quadratic formula again to solve for t. Okay, so this is going to be equal to negative 24.5 plus or minus the square root of 24.5 squared minus 4 times the first portion, so negative 4.9 times this last portion, negative 30.6. Okay, and that's going to be divided by 2 times a, which is negative 1/2 times 9.8. Okay, so let me go ahead and do that in my calculator. All right, so putting that into my calculator, I got 2.5 seconds. Okay? All right, so that's the time it takes for the baseball to reach maximum height. Okay? We could have also used another equation. That is the first equation here. V equals V naught minus G times T. And you can repeat this if you would like. Okay? All right. So the fourth part, part D, is what is the acceleration at the top of its path? Okay? So, we need to think about this logically. What is the acceleration at the top? You can pause to think about it for a minute. Okay, so hopefully you guys thought about this for a minute here. For part D, the acceleration remains the same throughout this entire process. So as the ball gets hit, goes to the top, and goes back to the bottom before it's caught, the acceleration remains constant. Okay, our acceleration is always going to be 9.81 meters per second squared. Okay? All right. The last question, I'm going to squeeze in right here if I can. It asks, what is the velocity of the ball when it is caught? Assume the ball is hit and caught at the same location. Okay, so that's y naught equals 0 and y equals 0. Okay, so we want to know the final velocity. And this is going to be at some time. Okay, it's going to be time equals 5 seconds here. Okay, so I'm going to go back to here and say, well, I can find my velocity with this equation. So velocity equals the initial velocity minus gt. So velocity equals my initial velocity, which was 24.5 meters per second, minus g, which is 9.8 meters per second squared, times time, which is 5 seconds. Okay, so plugging that into the calculator here, we get negative 24.5 meters per second. Okay, so this makes sense because the ball was thrown or hit and caught at the same location. Okay, so our velocity should be consistent with our initial velocity. All right, so let's go ahead and move on to finding our kinematic equations through the use of calculus. So we kind of did it earlier, but not a ton. So what I mean is, let's start with our acceleration. Our acceleration dependent on t. So our acceleration dependent on time is equal to our derivative with respect to time of our velocity. Okay, and we can solve for this in a different way. So we can say instead a times dt, I'm going to drop these for a second, equals dv. Okay, and remember in calculus, if we want to solve for our variable over here, we can take integrals. Okay, so we're going to go ahead and do that. So our integral of dv is going to be v, or a times some t plus some constant. Okay, and we'll continue this discussion in our next video.